what we have learned so far about black body radiation and its spectral density is that the spectral density is going to be the radiation is such that lambda max times T is a constant. In fact, what is true is that lambda any feature times T is a constant, and that feature we happen to take to be the lambda max, and this comes out to be roughly 2900 micrometer Kelvin. The other is the distribution formula which says that u lambda t is going to be of the form some function lambda t over lambda raised to 5, or of the form u nu t is equal to nu cubed, some other function. I may as well call it function f. This is not the same function as the one given above, nu over t. Up to this point, everything is exact, thermodynamically derived. The challenge is to find f nu over t, or equivalently that function f lambda t. So, Wien did a simple analysis and he got a distribution formula. What he said is, I'll just state this without any proof. He used something called the Boltzmann analysis. What Boltzmann says, and I'll come back to this again, that if there are systems that have energy E at temperature T, then the probability that a system that can take many energies, but has energy E, has energy E is proportional to e raised to minus e over k T. We will use it again. Temperature is T and K is known as the Boltzmann constant. All right, and this is equal to R over N, where R is the gas constant, and N is the Avogadro number. That is the value. So, the main point is the probability that a system has energy E, if it can take many values and it is at temperature T, is e raised to minus e by k T. So, for molecules in a gas, if they are freely moving, the probability that a molecule is moving with velocity v is going to be proportional to e raised to minus its energy 1/2 mv square over kt. Now, Wien made an assumption. Wien says that the radiation frequency emitted by a molecule is proportional to its energy. This is an arbitrary assumption just to get the answer. All right. So, the probability that molecule gives radiation of frequency nu is going to be e raised to proportional to e raised to minus some constant beta nu over k T. This is just an ad hoc assumption, and therefore, he says that the u nu T is going to be some alpha is a constant, times nu cube, because that is what his formula, thermodynamically derived formula, gave, e raised to minus beta nu over k T. Or in terms of lambda is going to be u lambda t is equal to some other constant, right, alpha bar over lambda raised to 5 e raised to minus beta over lambda k t, and there will be a c here. All right, these two formulas, where alpha bar may involve some alpha times c. Nonetheless, this is the formula he proposed, and you see this is of the same form. It has a nu over t here and lambda t here, exactly the form that he had proposed, but this is derivation is ad hoc. However, there are two constants here, right. So, let us just focus on this formula, two constants alpha and beta. How do we determine these constants? So, Wien's formula is that u nu t is equal to alpha nu cubed e raised to minus beta nu over k t. Alpha and beta are constants. How do we determine that? I already have two constants. I have sigma, which is the Stefan Boltzmann constant, and I have lambda max t, which is displacement constant. So, I can integrate u nu t d nu, which is equal to alpha nu cubed e raised to minus beta nu over k t integrated over d nu, and get an answer which will be proportional to t raised to 4. And I can also find d u nu t over d lambda equals 0, and that gives me where it is maximum, at what lambda is maximum, and through these two equations I can determine alpha and beta. So, he gave a formula, all right, and that formula turned out to be very good, right. If you see it experimentally, the true curve is something like this. This is lambda, this is spectral density, and the Wien curve fitted right on top, except when you went to larger lambda it became slightly smaller. So, conclusion, Wien's curve fits the experimental curve for nu over t going to very large value, but underestimates the curve for large values of lambda. And this is when, so the curve is very good. The Wien was absolutely on the right track, except that he was missing something. At the same time, there was another formula given by Rayleigh and Jeans, which said that the u nu t was 8 pi nu square over c cubed k t. How they got this formula, I will tell you in a few minutes, but let us see the two curves, how do they look. So, if this is the experimental curve, the blue one, Rayleigh Jeans is right on top, and when you reach large lambdas, let me see, this is lambda, this is, let us say, u lambda t, very good, and then it starts deviating. I am exaggerating it, but it starts deviating. And the Rayleigh Jeans formula matches beautifully out here, and but then it becomes large here. So, it matches only here, and this is Wien's formula. The true formula is somewhere in between, that should match everywhere. It should go to Wien's formula when you go to small lambda and restore to Rayleigh-Jeans formula when you go to large lambda, and that is where Planck came in and the quantization hypothesis actually resolved this, and that is what we want to do next. So, to understand how it comes about, let us first write what is going to be our line of attack as Planck did. We are going to assume that there are a lot of radiators which give out, a lot of oscillators and radiators inside, right, which give out radiation. So, a cavity is made up of oscillators giving out radiation, so that all this radiation fills up the cavity. And what we are going to show is that u nu t is going to be equal to 8 pi nu square over c cubed times E bar nu, where E bar nu is the average energy of an oscillator. So, what this does for me is, if we know E bar nu, we can calculate u nu t. All right. Now, this can be derived in many different ways. I am not going to do it because this is going to take time and it is slightly beyond the scope of this course, but if you are interested, I can send you material and I can explain it to you later, different forum. But the way it is derived are the two ways. One is to find the energy radiated by each oscillator and equate it to the energy absorbed by it from the radiation. You do that and you get precisely this formula. Second way is to count the number of modes that radiation has in the cavity per unit volume and multiply that by E bar. Both ways, this is the formula you get. All right. Now, what Rayleigh and Jeans did was they said E bar nu is going to be equal to k T by classical equipartition theorem, and that gave them immediately that u nu t is going to be 8 pi nu square over c cubed k T, right, which can be written as 8 pi nu cubed over c cubed k T over nu, and you see this fits the formula nu cubed some function of nu over t. All right. On the other hand, Wien says that u nu t is of the form some alpha nu cubed e raised to minus beta nu over k T. If I equate this to 8 pi nu square over c cubed e raised to minus beta nu over k T, it tells me that E bar nu is proportional to nu e raised to minus beta nu over k T, and truth is somewhere in between, and that is where quantum hypothesis comes in, and that is going to be the subject of the next lecture.